Acids and Bases, Part 5, Acidic and Basic Salts. After watching this video, you will be able to predict whether a salt solution, that is, an ionic compound dissolved in water, is acidic, basic, or neutral. You will also be able to calculate the pH of acidic and basic salt solutions. Because the conjugate base of a strong acid is such a weak base, ions like chloride and nitrate do not have an effect on the pH of solutions that they're in. These ions have virtually no affinity for protons. The cations of strong bases also have no affinity for protons, so ions like potassium and sodium do not affect pH either. As a result, salts that contain the cation of a strong base and the anion of a strong acid do not affect the hydronium ion concentrations of solutions. Aqueous solutions of potassium chloride, sodium nitrate, and potassium nitrate, for example, would all therefore be neutral solutions, having pH of 7 at 25 degrees Celsius. But let's consider a solution of sodium acetate. First, what are the major species in this solution? There would be water molecules, and because sodium salts are soluble, there would be sodium ions and acetate ions as well. Water is weakly amphoteric and would be the predominant producer of hydrogen and hydroxide ions if that were the only acidic or basic species in solution. Sodium ion, being the cation of a strong base, sodium hydroxide, won't affect the pH. On the other hand, the acetate ion, being the conjugate base of a weak acid, acetic acid, will have significant affinity for protons. The pH will be determined from the alkalinity of the acetate ion. Acetate will accept a proton from water to produce acetic acid and hydroxide ions. An equilibrium expression for the hydrolysis of acetate can be written as shown here, and the hydroxide ion concentration at equilibrium could be determined in typical acid-base equilibrium problems. Any salt with a neutral cation and an anion, that is the conjugate base of a weak acid, will produce a basic solution when dissolved. For example, sodium acetate, sodium fluoride, potassium nitrite, and potassium cyanide would all dissolve to form solutions with pHs greater than 7 at 25 degrees Celsius. So exactly how strong of a base is the acetate ion? The strengths of acids and bases are determined by the equilibrium constants Ka and Kb respectively. The Kb for the acetate ion can be determined from the Ka for acetic acid. In fact, for any weak acid and its conjugate base, the product of Ka for the acid and Kb for the conjugate base is equal to Kw, the ion product constant from the autoionization of water. The same is true for a weak base and its conjugate acid. The derivation of this relationship is relatively simple but not worth our time at the moment. This relationship can be used to determine the Kb for any conjugate base for which the Ka of the weak acid is given. Let's apply what we've learned to another straightforward acid-base equilibrium problem. What is the pH of a 0.30 molar sodium fluoride solution? The Ka for hydrofluoric acid is 7.2 times 10 to the negative fourth. Of course, we'll take a moment to consider the major species in solution. We have water, sodium ion, and fluoride ion. Only the fluoride ion will have a significant impact on the hydrogen ion concentration for this solution, because, as the conjugate base of a weak acid, it is itself a weak base, that is, a proton acceptor. The fluoride ion will react with water and come to equilibrium with hydrofluoric acid molecules and hydroxide ions. An ice table can be used, as shown here, to develop the equilibrium concentrations in terms of x, the extent of the reaction. For this reaction, we can write the equilibrium expression, but what's the value of Kb, the equilibrium constant? Since fluoride ion is the conjugate base of the weak acid hydrofluoric acid, the ratio of Kw to Ka for Hf gives us the value of Kb for the fluoride ion, 1.4 times 10 to the negative 11th. Substituting the equilibrium concentrations and making an appropriate approximation allows us to calculate the value of x. (2.0 times 10 to the negative sixth, which is the molarity of hydroxide ions in this solution at equilibrium. Our approximation is good because this value is much less than 5% of the initial fluoride concentration. So what's the pH? pH can be determined from the pOH. So the pH of this 0.30 molar sodium fluoride solution is 8.30. What about an aqueous solution of ammonium chloride? The major species in this solution would be water molecules, ammonium ions, and chloride ions. Again, water is weakly amphoteric. Ammonium ion is the conjugate acid of a weak base, ammonia, so it can act as an acid and donate protons. The chloride ion has no significant acidic or basic properties, so it's the ammonium ion that will determine the hydrogen ion concentration of this solution at equilibrium, and thus determine the pH. Ammonium ions produce hydrogen ions and ammonia molecules in this equilibrium reaction. A salt in which the anion is not a base, but the cation is the conjugate acid of a weak base, will form acidic solution. So solutions of ammonium chloride, ammonium nitrate, and iron 2 perchlorate, for example, will all be acidic, with pH values less than 7 at 25 degrees Celsius. What then would be the pH of a 0.10 molar ammonium chloride solution, given that Kb for ammonia is 1.8 times 10 to the negative fifth? Well, as we've already discussed, the major species are water, ammonium ion, and chloride ion. The ammonium ion, being the conjugate acid of a weak base, is itself a weak acid, so it will dissociate into ammonia molecules and hydrogen ions. From our ice table, we can write the equilibrium expression in terms of x. And we'll need to calculate the Ka for ammonium from the Kb for ammonia. By substituting and approximating and solving this equation for x, we can determine the hydrogen ion concentration, which is 7.5 times 10 to the negative sixth molar. The pH is the negative log of the hydrogen ion concentration, so the pH of this solution is calculated as 5.12. Our previous approximation also checks out because X was much less than 5% of the initial ammonium ion concentration. A salt that contains a highly charged metal ion produces a hydrated metal weak acid in water. Aluminum ion, for instance, will become surrounded by 6 water molecules, forming the hydrate aluminum ion complex. This complex, a weak acid, will dissociate into the positively 2 charged ion complex shown here, along with hydrogen ions. This occurs because the high charge of the metal ion polarizes the OH bonds in the attached water molecules, making the hydrogen atoms more acidic than they normally would be. Typically, the higher the charge of the metal ion, the stronger the acidity of the hydrate ion. So how could we calculate the pH of a 0.010 molar aluminum chloride solution? The Ka for the hydrated aluminum ion complex is 1.4 times 10 to the negative fifth. To begin, what's actually present in solution? There are water molecules, aluminum ions, and chloride ions. The aluminum ion is a cation of a weak base, so it has acidic properties. The aluminum ion will become hydrated. As a result, the reaction that produces hydrogen ions for this solution is the dissociation of that hydrated aluminum complex. Solving this equilibrium problem, as we would any other, allows us to use the calculations and calculate the extent of the reaction. We were given the Ka for the hydrated aluminum complex. So by substitution and approximation, we can calculate the hydrogen ion concentration. (3.7 times 10 to the negative fourth molar, which is about 3.7% of the initial acid concentration, so our approximation is good. The pH can be calculated from the hydrogen ion concentration at equilibrium. The pH of a 0.010 molar aluminum chloride solution is therefore 3.43. What about a salt solution like ammonium acetate solution? In this case, the ammonium ion has acidic properties and the acetate ion has basic properties. What would be the resulting solution? Acidic, basic, or neutral? We'll only look at this problem qualitatively, but if we compare the Ka for the acidic ion with the Kb for the basic ion, it will allow us to predict what kind of solution will be formed. If the Ka for the ion is larger than the Kb for the ion, then the solution is acidic. If the Kb is larger than the Ka, then the solution is basic. If the Ka is equal to the Kb, then the solution is neutral. Remember to compare the equilibrium constants for the two ions in the salt, and not the equilibrium constants for the weak bases and the weak acids that produce the ions. Otherwise, your answer will be the opposite of correct. Students often make this mistake because equilibrium constants for weak acids and weak bases are typically found in tables, but the equilibrium constants for the ions are not. In this video, you've learned how to predict and calculate the pH for aqueous salt solutions. If you have trouble with these topics, rewatch this video or review the associated pages in your textbook. Leave a comment if you have any questions. Thanks again.